All right, hell yeah. So what we got here is physics for scientists and engineers. Now it's hard stuff, and it just requires calculus. Everything requires calculus and crazy trick. So what we're gonna do is just simplify a problem. You get to a problem, you're just like, I can't do this one, and my brain don't work. But how do you actually just get the answer? You know what I mean? That's kind of the first step. Is just get the answer, and what we're going to use is a method called numerical method, numerical. I don't know. You just throw a number on it, change it a little bit, throw another number on it, and it gives you just a real good idea of what's happening. And we're going to throw it in Excel, so get ready for that. But let's just read it. We're going to read this all the way through. No, we're not. Okay, the mass of a particle right there. Booyah. It's 1 kilogram. That's 2 pounds. Okay, that's crazy because check this out. Just every time you do a problem, you should be like, well, how big is this thing? And it's crazy big. It's 1.2 meters. That's almost 4 feet. It's 4 feet from there to there. This is like 8. This is 8 feet. I mean that's insane. And then you're going to pull this thing this way, zero point 0.5 meters. Where's that? Right there. So that's only a foot and a half. You know what I mean? But this is a full sheet of plywood right here. This means it's like a tennis court. No, it's not. But it's not even a big room. It's a real small room. But I mean, this is you got springs on a 2 pound mass. I mean, this is ridiculous. But now that you actually visualize it, okay, you're gonna have two huge ass springs that are 4 feet long, and then you're gonna be pulling a 2 pound. Like, what's 2 pounds? And 2 pounds ain't very much. It's like a Nalgene. I mean, these springs are gonna weigh more than, you know what I mean. But whatever. Maybe. And this whole thing isn't like in the air. It's just resting on a table. Let's say. So cool. You're gonna pull. The 2 pounds is just an algae. You know what I mean? It's not much. Yeah. 32 ounces. 2 pounds. So you're just gonna be pulling like a 2 pound Nalgene bottle back, only a foot and a half, and then you're gonna let it go, and it's gonna go this way and this way. And do you think it'll go about that speed? Yes, I've already done this problem. You know what I mean? But if you, any of these problems, you should actually just kind of think about it. Be like, okay, if I actually did this in real life, what the hell is going to happen? I mean, because that's all you're doing with this equation. And the second you get this equation, guess what? You're going to be like, cool, I get an A. But no one really cares until you have like an understanding. And so we're just going to cross this equation out. But anyway, they want to use potential energy. So let's go to our Excel. And we're just going to type in energy. Because all energy is a Newton times is force times distance. So force times distance. Cool. All right. Now what's just force? You know what I mean? I mean, if you said this was force and this is distance, we better do force. And hell yeah, what's our equation? F equals ma. And what the hell is that? People don't even know what the hell this means. It means that if you can read it either way. I like to read it maybe like with the mass first. If I have a mass and I accelerate it, or I want to accelerate it, guess what? It's going to take a force. Or well, what's the other way to? Let's say I do have a force like gravity, and I let go of a mass. Guess what? I don't know what's going to happen. Oh, it's going to accelerate. Okay, cool. All right, so now we even have to define terms because we need to put what the hell's accelerate? You know what I mean? I graduated college and I still got to do this every single friggin' time. You know what I mean? Like no one knows what acceleration is, and it's just change in velocity. So acceleration is literally change in velocity. I guess we're just going to do a real slow problem. Well, we'll get to it. We'll get to it pretty fast, this problem. Okay, in acceleration, we say is A. Whoa. I hate when it tries to think what I'm thinking, and it's just totally the wrong thing. No, hell no. There you go. You got to put a stupid space. That's crazy. Maybe you don't. Do you just push A and then just tab? No, this is crazy. Like, no, you can't even push the arrow keys. It's just A and then space. And then let's say you do A space and then backspace. Oh, that's crazy. Just get an A in there. So A is meters per second squared. And another good way to look at this is just is literally meters per second and then per second. This actually makes more sense because this is your velocity changing every 1 second. So gravity, g is an acceleration, and that's 9.8. 9.8. This is a good comparison to be like, hey, do we have a lot of acceleration? Because I would say gravity is like, well, that's just 1g. 1g of accel. You know what I mean? And human body can take up to 10 Gs for like a few seconds, but it can really only handle about 5 to 6 Gs. About 3 Gs. You know what I mean? 3 Gs sustained is it. For a human, for NASA, you'll have to sustain 3 Gs, but you don't want to sustain 4 to 5 Gs. Hell no. Okay. So that gives you some values for what we're going to do. And for all these problems, literally, if you can identify the force, then you can identify the acceleration. And if you can identify the acceleration, then you can just figure out the change in velocity. Okay, so let's say I drop well, do we even need to do this? I'll probably do other videos on what the hell even. But let's say I just had this 2 pounds, this 1 kilogram mass, and I wanted to drop it, and I wanted to drop it for a second. Well, guess what acceleration says? Acceleration says that you're going to change, its velocity is going to change by 9.8 meters per second every second. So so if I drop this mass, it's going to go from 0 meters per second to 9.8, and we'll just call it 10, because half the battle is just kind of rounding in physics. Okay, just to even get the answer that we want. Okay, so we drop something for 1 second. 1 second of drop. And guess what? Its velocity was 0, now it's 10. But this is the thing to wrap your mind around in any physics problems. I mean, it's probably too much for your mind to handle, but this is the leap you have to make. You have to say, hey, was my speed always 10 meters per second? No. Was my speed always 0? No. Was my average speed somewhere in between? Yes. So you have this thing called v average, velocity average. Well, guess what? It's 5. And if you want to know the equation, it's this. It's 0 plus 10, and then all that divided by 2. Which is important because we'll probably use that. We'll probably use that in our calculation. You know what I mean? And that's going to equal 5. And just get this over here. But yeah, 5 meters per second. So now that you know our velocity average was 5 meters per second, how far did it drop? Because we dropped it for 1 second. If I drop you for 1 second and your average velocity is going to be 5 meters per second, guess what? You're going to go 5 meters. Okay, cool. So your distance is equal to 5 meters. Okay, and this is like super basic, but always start with gravity and kind of do a little, problem like this, because gravity is cool because it involves a force. Because the force is gravity, and really you should do this. I mean, if there's one equation to memorize, it's F equals got to put all this crap upstairs, but G, I guess we don't, but yeah, gravitational constant times the mass of U times the mass of the Earth, all divided by the radius from the center of the Earth to U squared. And guess what? The radius is just R is just the radius. R is just the radius of the Earth. Okay. And if you say, hey, this is, and if you say F equals ma, then you can say, hey, well, let's just throw this. This is our force. And booyah. That's the F. That's going to all equal your mass times your acceleration. Well, what do you know? The mass, this formula already has the mass of U, and that's going to say it's equal to the mass of U times your acceleration. So the next thing we do is just get rid of the mass. Get rid of your mass, because you can subtract them from both sides. divide them from both. Just get the hell out of both sides. That's all I'm getting at. And now you have perfect. And now you have your acceleration is mass of the Earth, gravitational constant, divided by the radius of the Earth squared. And we are like, I don't care if I'm doing long format videos, because every physics problem should kind of start with this basics, because it's like you can't just jump in to do a integral. And the only reason I'm not jumping in to do the integrals, I don't know how to do the integral. You know what I mean? But I'll get there. Next week I'll figure out how to do this stupid integral. It's such a magic trick. You know what I mean? The integrals. It's like juggling. It's not like juggling. It's literally a magic trick. All this crap's like juggling. Okay, so well, what's the gravitational constant? Well, just guess, but I think gravitational constant is 6,666. Just the devil times 10 to the negative 11. You should just remember that it's the friggin' devil. You know what I mean? And it's not. But the mass of the Earth, is that also a 6? I don't think so. Maybe it is. I don't think so. Yeah, maybe it is. I think it's 6. 6. Yeah, there's a lot of devils in this equation. 6 times 10 to the 24. And that's in kilograms? Or is that grams? No, it's kilograms. Does that even make sense? Yeah, 6 times 10 to the 24. A lot of 6s, like I said. And then, well, yeah. And then you got to all divide it by the radius of the Earth. And what the hell is the radius? You should always know the radius of the Earth. It's 6 million. It's 6 million, which is 6 times 10 to the 6. Look at all those 6s. Total, yeah. If there's any, that's a sign. That's a sign of the devil. Anyway, so and once you do this, if you simplify it, you got to square this. So this goes to 36 times 10 to the 12. Or let's just do this right now. Or this goes to or this just goes to 6 times 6. See what I did there? Times 10 to the 12. I think I said 24. No, it's just 6. You square it, goes to. Anyway, look at this. This 6 and that 6 divide into this 6 and this 6. You know what I mean? I mean, you can rearrange it. This is just 6 times 6, because this is the other part of physics. You know what I mean? Figuring out exponents. So now you got 10 to the negative 11 times and do we need to kind of zoom in on this? Nah, who cares? You can just make your screen huge as possible. But yeah. Oh, yeah, 10 to the 24. Okay, perfect. So, hell yeah. And then, so see how you're going to divide by the 6 over 6s? So the 6s go away. Now you have 10 to the negative 11 times 10 to the 24 divided by 10 to the 12. Okay, so let's say this was 10 to the 12. It's just going to be 24 minus 12. That's 12. But it's just minus less. This is equal to 10 to the 13. So you're basically going to have 10 to the 13. And then you're going to divide all that stuff by 10 to the 12. Now, I don't think I did this right at all. That's why I really shouldn't be doing stuff. Well, isn't gravitational constant 10 to the negative 11? And why isn't that working out? Oh, yeah. I don't know why. Oh, no, perfect. Yeah, we got it. Guess what? 10 to the 13 divided by 10 to the 11. Guess what? That's just 10. And what the hell did we even solve? You're probably just like, what the hell did you even solve? Well, you solved for A. See how A is over here? And you throw in gravitational constant, it's the devil to the negative 11, and then 6 times 10 to the 24. I don't know, just pick your NFL favorite football person that's got a jersey 24, and you can figure out the mass of the Earth. But it's just all these 6s. Look at this. And this is 6 times 10 to the 6 squared, and 6, 10 to the 12. Anyway, you do all that and you get 10. And what do you get? 10 meters per second per second. You know what I mean? Yeah. So what we did there is like we didn't just start out with giving you G. You know what I mean? G is 9.8 meters per second. You know what I mean? We made ourselves work for it, and it's so there you go. It's 10 meters per second per square second. That's G right there. That's G, baby. Okay. Anyway, but what we did there is that we used Newton's law. Newton's law says F equals ma. And you might think, hey, if there's a force, you put it, like, what side? See, this is the crazy thing. You have to identify the forces. This is the sum. F equals ma. Let's write it again. F equals ma. So it's the sum of the forces is equal to whatever your mass you're doing, whatever mass you got times its acceleration. So if you can sum all the forces and then divide by mass, then you get acceleration. So let's just do that. Acceleration is the sum of the forces and then divide by its mass. Perfect. And why do you want to find acceleration? Because perfect. Let's do this. Acceleration, change in velocity divided by change in time. Booyah, booyah. And I like to do delta. I don't know how to do symbols on here, but delta, is the little triangle. It's a little triangle. Delta V over delta T. Now, some people will say delta means a very small amount. I say screw that. Make it as big as you want because it's just an average. You know what I mean? It's what we did right here. We said, hey, in 1 second, our change in velocity was what? Our delta T was 1 second, right? 1 second. And our change in velocity was 10 meters. 10 meters per second. So, because we changed our velocity from 0 meters per second to 10 meters per second. All right. But the other part of this, and we got to do A is equal to. But anyway, the other thing that you might see is A is equal to dV dt, and that'll just make your head spin. Still, you can just think of the delta V and the dV about the same. I like to consider this just like an average. You know what I mean? Hell, my delta T is 1 second, good enough. For this problem, hell no, because it's going to take a whole second to get to here. We actually have to break this up into tenths of a second, hundredths of a second, thousandths of a second, and we can do that because we got Excel. But see how there's a difference there? If we just say, hey, if this mass is over here, and then in 1 second later, what's its change in velocity? Well, it's too big of a leap. Now, what am I getting at? If for gravity is constant. Gravity near the surface of the Earth, I should say, near the surface of the Earth is always 10. It's always 9.8. So that has a constant force. So if this was just gravity pulling it this way, and it took 1 second to get here, we already did that. It's going to go from 0 meters per second to 10 meters per second. So now, just like we actually just like took the Nalgene's and took the springs and kind of just mentally visualized this one in our head of like how fast a Nalgene is going to go, whoop, and back and forth. How fast is it going to go? And we did a pretty good job because it takes about I think it takes about a second to get from here to there. I don't know. Maybe the answer in the back of the book, if you just want to know, the velocity is going to be 0.83, 0.832, 0.823, 834. I have no idea. It's something like that. But anyway, meters per second. So now what you should do in physics is like you literally just want to start with guessing. So see, even just right here, we got F equals ma. So and this F equals ma is like, hey, can you identify a force? And there's only a few forces in the universe. Like literally, one is gravity, and two is a spring. You know what I mean? 3 might be like electricity. I don't know, like electromagnetic force, just magnetism. But anyway, so this spring is going to have a force. Now, it's crazy because even springs, they're so simple, but yet they drive me crazy. The force on the spring is just equal to, I'm just going to say this, force is just equal to how much you pull the spring. How much you pull spring. And better said, force is distance you pull spring. And I would do this. Force is double if you double the distance you pull spring. Cool. You know what I mean? Force is triple if you pull the spring 3 times as much. So anyway, and then spring, always has a Newton equilibrium, neutral. Always has neutral. Neutral equals no force. Okay, so we're just kind of giving ourselves what is the actual equation for the force of the spring. It says, hey, force of the spring is the spring constant. That's where your mind explodes. You know what I mean? I don't like that K at all, but it's actually real simple. And then it's D. Force is equal to KD. It's like, hey, if they give you the spring constant, what's the distance that you pull it? That's going to be the force. It's probably, I don't know what's going to be simpler for you. I think it's simple for me if I say it's KX, because distance is always like, in the X direction or whatever. Like right here, look, you pulled it in the X direction. Cool, so that's that X. And the spring constant, so it's 40 Newton meters. And can we get that? First chapter of physics. So anytime you do a physics problem, you can relate this to the first and second and third chapters. First chapter of physics says, hey, your force is in newtons. So we you know what I mean? Force is in newtons. Perfect. And that's going to be equal to mass in your kilograms. Kilograms, it's mass times acceleration. Mass times acceleration, which is equal to kilograms times meters per second squared. Okay, cool. And that's literally newtons equal to kilogram meters per second squared. But in ours, they say force is just they just say force is kx. So we'll write that one more time. That wasn't faster. All right, force is just kx. So we're going to write that out. So force is newtons. Force is in newtons, and then is equal to k. We don't know k. You know what I mean? We don't know k. So we're just going to write this. We don't know it. Times, well, we do know x. X, hell yeah. X is just meters. I'm pushing the wrong button. Okay, there you go. So if newtons over here times something with meters, what's this k? Well, k is just going to be a so what times meters gives you newtons? Well, I would say Newton divided by a meter. Newton divided by a meter. Cool. Okay, cool. And I guess I did it this way because check this out. This says Newton is equal to kilogram meters per second squared. So we could actually replace this Newton with kilogram meters per second squared. And K. K could also be, it's never going to be written this way, but it could also be kilograms times meters per second squared. And then you actually divide it by this meter, so that'll get rid of this meter. So you would have kilograms per second squared. That would also be K. I feel like I didn't do that right at all, but no, we did. Because if K is newtons per meters, you throw in newtons, kilogram times Newton, the meters cancel, but divided by second squared. So yeah, so K is also that. But anyway, so but K is just spelled out. The constant says, hey, the force divided by the distance, and then give me your distance. You know what I mean? Because if I give this K, if I take a newtons divided by meters, I don't know why I'm pressing this god darn different button. But then I give it a distance, and I give it a distance m. Guess what? The m's cancel, and all I'm left with is newtons. Hell yeah. And that's what we want. Newtons of force. Oh, I did not like that at all. Left with newtons. Cool. Try to get better at that key. There you go. Perfect. And the cool thing, like I said, if you can identify the forces, hell yeah, if you can identify a Newton, whatever had mass, this little ball, this little Nalgene had 1.18 kilograms. If I can identify that, guess what? We're going to have an acceleration because there's no rope on this holding it back. But if there was a rope holding this back, the force would be equal. But right now this is not equal. The forces are pulling it this way. They're actually pulling it this way and this way. But we're going to basically have a net force in this direction. That should be super obvious. But if you have a force in this direction, guess what? We identified a mass, we're going to get acceleration. What the hell is acceleration? Change in velocity. So if we pull this back and let go, our velocity goes from 0 to some sort of change in velocity. So the cool thing about this is that we can at least just guess. So like right now, we can be like, oh, well, these springs, see, here's the other thing. You have to go back to the springs. Springs only work if you pull them or push on them. So springs only work if you pull, push on them. And probably a horrible word choicing because, I mean, we're on the chapter of work. So what the hell is work? We actually have to define that. Work, I didn't want all caps, but it's all right. Work is newtons times distance, times meters. Okay, so that's a force, which we've talked about a lot in this, and then it's just times distance, times meters. So let's say this ball was neutral, and I had to pull it back with like a force, you know what I mean? And a force could be weighed in pounds. If I had a scale and I pull this back, and let's say I just have to pull it back at a constant force, and I pull it back 1.5 meters. And let's just guess. How much force do you think it's actually going to take to pull this thing back? That's the other thing. I mean, if I literally set this up, 4-foot springs, that's insane. That's insanery. But anyway, and pull it back a 2 pound. So I'm just pulling it back. I can't imagine there's going to be more than 2 pounds on the ball itself. Let's just do that. I think it might be up to. I think that's a pretty good guess. Yeah, I don't want to divulge what I know from yesterday doing this problem, but anyway, I'm just going to say there's 2 pounds. So now the next thing, you have to convert everything to Canada. You gotta. You don't need a passport. You just buy your weed when you get there. But anyway, you need, what the hell is a Newton? A Newton, yeah. So 1 Newton is a McDonald's hamburger. And I can say that because I don't shop at McDonald's for my food. But anyway, and so that's quarter pound. Cool. All right, 1 Newton. All right, so if 1 Newton is a quarter pound, 2 pounds, well, that's going to be 8 newtons. Maybe you didn't know that, but anyway, we got 8 newtons. Let's do it over here. 8 newtons. Perfect. Okay. And cool, we have our force. We pulled this back, and so work says that we pulled it back 8 newtons. Oh, and work is also in joules. So joules is the literal definition of newtons times meters. So if you pull something back 1 newton, which would be a quarter pound, and you pull it for 1 meter, you got 1 joule. But we say we're pulling 8 newtons, and we're pulling 1.2 meters. I can't do math. Oh, what the hell? Let's say we pull it back 1.5 meters. Okay, so it's going to be 8 times 1.5. That sounds like 12. You know what I mean? And I'm just going to guess, looks like we're going to pull this 10 newtons. 10 joules, sorry. So if we pull this, if we pull on a force, so let's do it. So work is equal to the force times the distance. So it's going to be 8 newtons times 1.2. 8 times 12. See, I don't know what 8 times 12 is. I do know what 8 times 6 is. That's 64. I hope it's 64. So it's 128. So 8 times 12. No way. 8 times 4? No. 8 times 6. 8 times 6 is 48. Good Lord. Yeah, I was losing my mind because it's closer to 100. It's 96. Okay, so you're going to get 9.6 joules. Cool. Because 8 newtons, pulled it back 8 newtons, capitalize that, and we pulled it 1.2 meters. All right, hell yeah. And we got 9.6 joules. Cool. And that's all this equation is. This equation is in Newton meters. So I don't know. You know what I mean? I think we can just write that right here. So newtons times, messing up. Okay, Newton meters, joules. All right, this equation is in joules. So x is in meters, and L is in meters, and K, we already did that. It's going to be newtons divided by meters because you're going to times by a meter to get newtons. All right, so now that we even just did this, it makes their spring constant just. They're just giving you this. Springs are literally just giving you the force, but the only crazy thing about these spring problems is that the force is always changing. Gravity is always the friggin' same if you're close to the Earth. Even if you're skydiving, it's still 9.8. Don't fool yourself. But anyway, but yeah, with a spring, holy Toledo. If the ball's here, there's no force. If the ball's here, you know what I mean, you're going to get some force. Now, if the ball's halfway, is the force half? Maybe. But it's not, you know what I mean, because of geometry. But you could just say, sure, half. It's half. Okay, so now the next name of the game is to actually just let's get any number for this. And this is what I could have started my podcast with. Hopefully, but anyway, but this is sweet. So now I would do the guessing. You know what I mean? And even right now, I'm like taking my time, but I do know how. I do know how to do this because when this ball is here, these springs are L, 1.2 meters long, and they're in equilibrium because it even says that. The equilibrium point is x equals 0. And it says assume that it doesn't specifically say that these springs at 1.2 meters are in equilibrium, but it does say that the equilibrium point is 0. And, if the springs weren't at their most relaxed, even if there was tension in the springs, there still could be tension in the springs, but I guess that doesn't matter. Oh, yeah, so I'm answering my own question. So even if you tension these springs, hook it to the ball over here, tension this spring, hook it to the ball over there, that's irrelevant. Because once this ball is here, there's still no force. There's no movement because the force is equal on both sides. And the whole idea of a spring is once you pull it a distance, then you introduce a force. And the cool thing, okay, so with this problem, so let's say these springs, let's say you actually put 10 pounds of tension on this spring, hook it to this Nalgene, 10 pounds of tension and hook it to this Nalgene. That force is going in this direction, in the Y direction, and they're equal and opposite. And so this ball should never go up and down in the Y direction because these forces are the same. So even if you pull the ball out here, yes, now you're going to have, if it was 10 pounds pulling this way and now you stretch the spring, you're going to actually have more than 10 pounds. Let's say it's just 15. Now you have 15 pounds pulling this way and 15 pounds pulling this way. Cool. The ball ain't going to go in the Y direction. But because you have 15 in this direction, that means like you still have the original, I don't know. Maybe you have 12 pounds in this direction and then 3 pounds this way. from this spring, 12 pounds in this direction, and then 3 pounds this way. So you actually have a net force of 3 pounds pulling it this direction. And if you have a force, again, if you have a force, if you can identify the force of 3 newtons, or 3 pounds would be 12 newtons, 3 times 4. Let's just do that, 12 newtons. And our thing's about 1 kilogram. So that's going to be equal 1 kilogram times acceleration. And acceleration, as long as you're using newtons, kilograms, and meters per second squared, this is going to say, well, it's going to have A is going to have to equal 12. So A is equal to 12 meters per second squared. Now, this isn't anywhere close to this problem, but it gives you just an idea of what's going on. And that means that once you release this, it's zero velocity, and in 1 second later, let's say it takes this Nalgene 1 second to get to here, is going to be going 12 meters per second. That would be hella fast. It's 24 miles an hour, and obviously that's too high. You know what I mean? Okay, so let's do what we have. But that's cool. I at least identified that these springs don't have to be neutral. So when you buy a spring, it's kind of at rest. It has a neutral length, but that's irrelevant as long as springs can stretch up to a degree. As long as a spring doesn't get sprung, as long as you're not pulling on a spring where you're actually just damaging it, and just like stretching it out. Where once you release it, it doesn't go back to its original shape. Then you put too much fatigue into the spring. As long as the spring always goes back to its original shape and you're within the range of a spring, yes, if you double the distance, then you double the force. You know what I mean? So let's say you pull the spring 1 inch and that took a pound, then 2 inches is going to take 2 pounds. 12 inches a foot is going to take 12 pounds. All right, so let's get to it. So when we now we got to do the trig, which kind of sucks, you know what I mean? Because when we pull this, and sometimes anytime you're dealing with trig, it's kind of good just to guess. So I'm going to say, hey, this is 4 feet right here. We're going to pull this back 1.2 meters. How much do you think this lengthened? You know what I mean? Literally, this picture is wrong because it actually shows it being pulled back. Because L, look at this. Where the hell's L? See, I didn't even read this. Oh, no, yeah. I'm getting confused with meters and feet. I said this is 4 feet, but yes, this is 1.2 meters. And I got confused with how far you pull this back. It's at 0.5 meters because I was saying I ran into this problem yesterday, and you're going to run into this problem all the time if you're trying to figure out like what the hell's going on in feet and pounds, because you're always going to be converting from you're going to be crossing the border. You got to go to Canada. It sucks. But meters are amazing. Meters and meters per second. Everything in meters, everything in kilograms. It makes physics just so much easier. You do not want to do physics because no one knows what a slug is. And go, there's like one video on YouTube. Go right now. Figure out what the hell a slug is. Because it's anyway. I don't even want to. Yeah. You'll surprise yourself of how little you know about America. Okay. Anyway. Yeah. I was getting ahead of myself. So yeah, this is 1.2 meters, and I'm going to pull it back 0.5 meters. So yeah, it would be about halfway, just a little bit less than. It'd be a little bit less than, because this would be 0.6, so this would be 0.5. The ball literally should be right there, or it's a particle. You know what I mean? It's an Nalgene of water. It's 2 pounds. It's about 2.25 pounds. Anyway, 2.5 pounds. Okay, but it's right here. So how long do you think the spring lengthened? It went from 1.2 meters. So that's where it's kind of like, I guess we got to deal with meters. So did it go from, see, that's why meters don't make sense to anyone. Like 1.2 meters. 1 meter is about 40 inches. So 1.2, well, let's say it's like 50 inches. And I just pulled it back 20 inches. So 50 inches, pulled it 20 inches. How many inches did this thing lengthen? I mean, you think it lengthened 4 inches? Because that would be only a tenth of a meter is 4 inches. So that's the other conversion that you should know. I mean, so 1 meter is crazy. It's actually closer to 40 inches. And why is it closer to 40 inches? Because 100 millimeters is really close to 4 inches. And 1 meter is just 1,000. 1 meter is 1,000 millimeters. So anyway, so yeah, a 1 meter is way closer to 40 inches than it is a yard. You know what I mean? So that's the first thing. If you're doing physics and you're converting back from meters to inches and standard, it's closer to is way closer to 40 inches than it is a yard. Put it that way. Okay. So yeah, so our spring is only going to lengthen. So finally we freaking got to it. I apologize, but our spring lengthens 0.1 meter. But now, because our spring lengthened, we can find a force. Because the whole idea from the force of a spring is just this K, this 40 newtons per meter, which is your, anyway, and the distance that you pull the friggin' spring, the 0.1, you know what I mean, 0.1 meter. So all that crap cancels, and you get 4. So 4 what? 4 newtons. All right, and didn't we say 4 newtons is about a pound? Cool. Yeah, it took a pound to pull this back. Okay, or 4. Okay. This is probably the last time. I'm just going to kind of stick with the metric scale. So yeah, you're pulling it back 4 newtons. The thing weighs. Go back to here. The thing weighs 1.8 kilograms. We're really just going to round that right now to 1 kilogram. So let's get back to our F equals ma. Force is 4 newtons. Well, let's write it out. 4 newtons is equal to mass, 1 kilogram, times the acceleration. So the acceleration has to be 4 meters per second squared. Cool. And what the hell does that even mean? It means we're going to have a change. Like we said, acceleration is equal to change in velocity divided by change in time. And I don't mind using the d here, just don't confuse yourself. Don't think we're doing calculus. No, it's just, we're just using nomenclature. We're just using dv dt to say, hey, I'm going to change my velocity, and I'm going to change, we're going to have this much change in velocity over this much change in time. And typically it's like just 1 second. So I'm going to have a change in velocity of 4 meters per second over 1 second. And let's just say it takes 1 second. So now we know that our velocity could be 4 meters per second right here. It could be if it took a full second. I guess it doesn't. Well, it's not that it doesn't, but the thing is about these springs, let's just get to it. As I said, the force when I let go of this is going to be 4 newtons. Like that is a 100% guarantee. That literally is the definition of the force. Oh, see, we already messed up. One of these is lengthening 0.1 meters. So there's 2 springs here. So our force on both of them is 8. And we'll take this over here, and this becomes 8 newtons. And our change in velocity is 8 meters per second. And let's just say it took 1 second to go from here to here. Well, didn't we say the answer in the back of the book is 0.834? And we're already getting 10 times that. So what gives? You know what I mean? I mean, it was a good attempt, but literally we don't know what the distance it travels. All we know is that the acceleration. So now we're going to do this because this is one with physics. Didn't we say we dropped something for 1 second and it changed its velocity 10 meters per second? So this is the other equation. We're going to do it crispy. So this is 9.8 meters per second squared, and you integrate it. And if you why do you integrate it? Well, let's just do it. Acceleration is dv is the change in velocity divided by change in time. Okay, so now you can take a times, you're going to take the dv and bring it upstairs on the other side. So now you have a times dt is equal to dv. Okay, so now, like, does that make sense? No. But now you're just going to rearrange. You're going to rearrange this, and you're just going to A times dt, which is saying dv is just, and then throw in A. A is 9.8 times dt. Perfect. And now you integrate both sides, and now you get v is equal to 9.8 9.8t. And this is also dv is equal to 9.8 times t to the 0, because there is no t. It's not a function of time at all, but it's t to the 0 times dt. Now when you integrate this, now you're going to get 9.8 to the 9.8 times t to the 0 plus 1. This is the how you integrate, and then you're going to divide all that crap divided by 0 plus 1. I mean, it's just that might not have made sense at all, but that's literally how you do integration. Basically, 9.8 integrate a constant. It's 9.8t, 9.8x. But anyway, now you do the same thing, because what the hell is velocity? Velocity is just the change in it's just the change in position divided by change in time. So it's cool because you get to do this process twice. So now you're going to go v times dt is equal to dx. Rearrange this crap. Okay. What, did I do it right? Hell yeah. And then now insert what the hell the value of v is. Value of v is 9.8t. 9.8 times t. And then times dt. Perfect. And if you do this a little bit stronger, it's 9.8 times t to the 1 now. T to the 1. And this will just help you with your integration skills. Because now we integrate both sides. Dx just becomes x. Gives us our equation for position. And that's going to be 9.8. 9.8 times t to the 1 plus 1, which is 2. And then you have to divide all this by 2. I mean, does that make sense? I mean, it's just how you integrate, 9.8t, integrate 9.8t, it's a 9.8t squared divided by 2. So blah, blah, blah. Anyway, 9.8 divided by 2 is 4.9. So now we have 4.9 t squared. Cool. So now we have our position. And, I mean, let's throw our and in this, I mean, the other bummer that I didn't do, this is 9.8t plus a constant. But what the hell does this constant mean? And it should be capitalized. All right. This constant says, hey, when your time is 0, your initial velocity is c. But, anything starting from rest, at time 0, our velocity has to be 0. So it's 0 plus 0, c is 0. You know what I mean? Blah, blah, blah. Cool. But now, over here, when we integrate it for position, you're going to get this plus another c, c2, we'll call it. So another constant of integration. And this says when your position is 0, so throw a 0 right here. No, I'm sorry. When your time, well, two things are happening. Yes, when your time is 0, our position, oh, so this is cool. This is cool. Because in this one, our time is 0 and our position is 0.5. So C2 is 0.5. There you go. There you go. Because when our time is 0, this is going to be 0. All this crap's going to be 0. But our position is 0.5. Okay, hell yeah. Hell yeah. I mean, right here we just did it for a falling object. But if we said, hey, are all objects falling out of the sky this way? Blah, blah, this would work. So now we do that same thing, but instead we throw in the acceleration that we got. This was not it. This was just a first guess. So our acceleration was oh, and this should be 8. Our acceleration was 8 meters per second squared. Okay, so now we're going to throw an 8 right here. And we're going to integrate, and we're going to get this to 8. That to 8. All right, looking good, looking good. All right, this becomes 8. Another 8. Okay, and yeah, we got to divide that by 2. So instead of 4.9, we're just going to get 4. Whoops. Okay, so now we have an equation for position if our acceleration is constant. You know what I mean? That's why anytime you do a problem, this is the wrong answer, but at least it says, hey, when we let go of this, it's going to have a force. Oh, see, here's the other thing. This is why I like doing these problems and running into all the hiccups along the way, because this 8 newtons of force is literally no, and it let's see. I'm going to retract my statement that says I'm just going to assume these springs are at a neutral position. I can't confirm or deny that if they're not in a neutral position, if they're not neutral and there's tension on them, and then you pull it this way, it seems like there's going to be more tension, even though you're just pulling. You're only lengthening the springs. I mean, the equilibrium point is here, so it still doesn't seem like it matters if there's a tension in the strings. But I am definitely going to say there's zero tension in the spring when this particle, this Nalgene, is right here, this ball or whatever. And then when I pull the spring this way, the spring lengthened 0.1 meter, which we said was 100 millimeters, which we said was 4 inches. So this whole spring, you know, which we said was almost 4 feet, this 4 feet spring lengthens 4 inches. Okay, got it. And we said that lengthening, due to the spring constant being 40 newtons for every 1 meter, but we only lengthened 1/10 of a meter, so we get 4 newtons of force out of this spring, 4 newtons of force out of this spring. But the force is almost more in this direction. We said this particle is actually like right here. So all the force is pulling this way and all the force is pulling this way. And only a component of that force is pulling this way. So, I mean, if we just look at our diagram, it looks like, well, hey, there's 1 meter here, a half a meter here, and the force is pulling in this direction. So it looks like it's only half that. So let's just use that as our standard and say that. But actually no, because we will have to figure that out. But it's literally just whatever component of that force is this way compared to this way. And I mean, it's the same as distance because distance is also a vector. If I say, hey, the distance from here to there, well, that's also the distance from here plus the distance to there. So distance is also a vector. So a velocity or a force, so even if this was a velocity, the velocity is going this direction. Well, it's got a component of the velocity in this direction and component of the velocity in this direction. And I hate this diagram because they made this x too big. This x should be right here. But anyway, and your Pythagorean theorem is your first thing that you need to know for any trigonometry. It says that this squared plus this squared is the hypotenuse. And a vector is truly always a hypotenuse, you know what I mean? Unless you're just going in one direction, you know what I mean? Like you know, back and forth on the x-axis, you're always going to be kind of going at an angle because you're going to be going like a component in the x and a component in the y. You know, vectors are always going to be, you know, I mean, because if you have something that's just going in the x direction, well, the y component's irrelevant, and you just got a one-directional problem. So everything's going to have like an angle to it, and it's going to have a component in the x, component in the y. And your first equation is going to be x squared plus L squared is equal to this hypotenuse squared. Okay, so that's how we got that distance. So we should just do that right now. So let's say x squared. I'm kind of guessing and going back. So that's how it's like I start with a guess of something that I know, or just estimate, and then once my mind kind of settles in to that being evident and obvious, then it helps me with the very specifics, like this Pythagorean theorem. And then we can say it's the square root of all this. So we're just going to take the square root of all that. And what the hell does that give us? The hypotenuse. So we're just going to the hypotenuse. Cool. And we're going to give this, we're going to say this is L2. You know what I mean? This is the length of the spring after it went 0.5 inches. So we're going to write this as an equation. So we're going to go square root. I didn't have to capitalize that. And then, but now we need to throw some values in here. So our x is 0.5 meters. Our L is 1.2 meters. Cool. And that's it for this one. So our L2 is equal to square root of x squared. Now, do I need a parentheses? I mean, I usually get parentheses crazy, but I don't want to. I just want to see if this is, it's perfect. It's 1.3. And we want to know the change in length of the spring. So it's delta L. I don't know. Maybe you don't like that. Maybe you don't like that at all, but it's just change in length of spring. I mean, because anytime you use delta or like a caret, I do like it now. Delta V, delta T, and this dV dt. This is like an infinitesimally small, but who cares? Well, let's say you don't care if it's infinitesimally small. And then delta V, I like to think is not infinitesimally small. It's kind of like a guess. Hey, I'm just going to do an average over 1 second. My velocity is going to change 10 meters per second over that 1 second. Now, my acceleration for gravity is constant, so it's always going to be 10 meters per second. But in our case, the force on this, or the acceleration, is going to be max right here, and then just a moment later, the force on these springs is going to be less because they shortened, and then it's going to even be less. And then once the particle gets to here, there's going to be no force on the spring. It's still going to have velocity, so it's going to travel this way until the springs start to do the exact opposite. They're going to be starting to slow this puppy down, and so you're going to have something that goes slow, fastest, and then back to slow. Stopped, slow, fast, slow, stopped. Slow, fast, slow, stopped. And that's your oscillation back and forth. Anyway, so our change in length of the spring, well, that's just the length of the spring. That's the, it's the absolute value. You know what I mean? Because we're going to say it's just the length of the spring minus the change in length. You know what I mean? And but anyway, you want this to be well, I mean, let's say the spring got shorter. Springs can get shorter. That means the force is in the opposite direction, because that's the other crazy thing. This is actually F equals negative K D. And what the hell does this mean? It means that if you pull on a spring this way, so I pulled on the spring this way, and the force is going to be, so that the spring was here, I pull it to here, the force is going to be in the negative direction, because I already said that this is the x direction. Let's say this is the positive direction. So let's say I just have a spring in this x, on this x direction, and then I pull it where x is positive. So my d is a positive, but guess what? The force on the particle or the spring or whatever the spring's pulling is going to be back in the negative direction. So that's why this force is negative. But I honestly don't like terminology like this. It's better just to draw pictures and be like, okay, use your intuition. I'm pulling on the spring, and it's going to be this direction. So I mean, because let's say this. Let's say you did use your F equals ma, and then your acceleration said it was going in, well, like we did. We actually got an acceleration of 8 meters per second, but we just assumed it was going this direction. You know what I mean? But actually, that should be -8 because this is the positive. So if this particle is going 8 meters per second in the positive direction, it's going that way. But no. It's going -8 meters per second. And once it crosses this equilibrium, it's actually the acceleration is pointing this direction in the positive way because it's slowing down. Once it gets to here, the acceleration is still in the positive direction until it passes this equilibrium point again. All right. Hell yeah. Okay, so we got our yeah. So that was 100% accurate, and now we're going to yeah. So our force was definitely 8 newtons, but our mass was not 1 kilogram. It was 1.2. So our acceleration right here, we're just going to do equals. It was going to be 8 newtons. 8 times 1.2. All right, so we got 9.6. Yeah, that's a difference. 9.6 meters per second. And that's cool because that's gravity. So this thing starts out being pulled by gravity. 9.8 meters per second. Because did I do that right? Our spring lengthened 1 meter, and we had 40 Newton meters. So that's going to be 0.1 times 40 is 4 newtons. And there's 2 springs. Oh, yeah. Back to reality. Yes, back to where we were at. So yeah, you have 8 newtons times 1.2 because you identified your force. We know our mass is 1.2, and you need to find the acceleration. And I already did this wrong because our force is 8 newtons, our mass is 1.2. We need to find the acceleration. So acceleration is this force divided by 1.2 kilograms. And that's going to be equal to 8 divided by 1.2. What? All right, so there you go. So there is our meters per second squared. There's our acceleration. So this is all garbage. Catching our mistakes as we go. And this is the combined force on both these springs because we took this 4 newtons, doubled it to 8. But the component is in this. The acceleration is in. It's like. I guess we should just half this and say one component's in this direction, one component's in this direction, so the acceleration is equal in the y, but you're going to have a net in this direction. Or, you know what I mean? It's basically just yep. So so anyway, you use the trick is to use this Pythagorean theorem backwards. Let's see. How the hell? Oh. Yeah. In this problem, we don't need to do sines and cosines. You know what I mean? That's maybe for another. But you do need to know what tangent is. You know, so I'm not going to go over sines and cosines. I don't want this to be like a 4-hour video. But you do need to know what tangent is. Well, tangent is just sine divided by cosine. So maybe you do need to know what sine and cosine is. But tangent is just like let's say this is our angle right here. You know what I mean? Because that's kind of the angle that if I pull this out way far, it gets real small. If I just pull it out a little bit, it's almost that angle is basically 90 degrees. Okay, so tangent says what the hell does tangent say? I actually forget. Oh, whoa, but I don't because tangent's sine over cosine. And what the hell is sine? Let's say I have this angle right here. Well, sine of this angle is you just think sun shining. The sun's going to rise over here. You know what I mean? So the sine of this angle is going to be this length. And so let's just do it. Sine of the angle, I don't even know what the hell to do for angle. Sine of the angle is equal to L, but that's going to be over K. You know what I mean? Or over L2 for what we're doing. Let's say we're just doing the length. Okay. And okay, now let's do this. We are doing sines because okay, so when we start at the 0 point, this angle is 90 degrees, and L2 is just equal to L, and that's important. That's important. You know what I mean? This is the crap all the professors just skip. They're just like, oh, you should figure out how to do sines and cosines. Well, just take 5 minutes and explain like what you know about sines and cosines. Because when sine is 90, that just means sine of 90 is 1. But what that's saying is basically that's saying this length is the same as this length. Cool. Well, how about when I go take this to infinity? Isn't that going to mess us up? You know what I mean? Well, no, because if I take this way out to infinity, that's just going to be the sine of 0. So if I say 0 is here, well, 0 is equal to a real small number divided by a huge number. So if I have 0, so 0 is equal to, or just any number, we're just going to call it n, divided by infinity. You know what I mean? That's 0, and that is what's happening. But the other cool thing here is that sine of 90 is just 1. So you're going to have 1. So this whole idea of sine and cosine, we'll get to cosine in a second, is literally just a fraction between 0 and 1. So literally, if you see sine of an angle, you're going to get a number between 0 and 1. And that's usually like 0.1 or 0.3 or 0.8. But it doesn't matter. It's going to be between 0 and 1. And if you think of these as percents, 10%, 30%, and 80%. Perfect. Now you know that all sine means is a percent of what? It's a percent of this length. And from an engineering perspective, it's the vector that you already know. You know what I mean? Typically it's this you already know. You know that the acceleration is in this direction, like we said, 6.6. But we don't know is what component of that acceleration is this way. But because we're using either sine or cosine, because the other thing is cosine. Let's just do cosine is this. So cosine says that this length, x, divided by the hypotenuse, and we'll do the same thing in a moment. But still, it's still a fraction between 0 and 1. So it's saying that if we know this length is now 1.3 meters, what is, and we know this angle, you know what I mean? Let's say we just know this angle. This angle is going to be about 60 degrees. Cool. And what do we know about cosine of 60 degrees? And maybe you don't know this, but cosine 60 degrees is 0.5, is 0.5. And what the hell did we say? So what does that even mean? Well, that's 50%. You know what I mean? So just think of it that way. 50% of what? Well, it says that this length in the cosine direction, adjacent, you know what I mean? Hoodlum in the alley, adjacent, I don't know. Yeah, I do sun shining, this is the sinin. If the angle's over here, this is the sun shining, and this is the hoodlum in the alley that doesn't want to do math or physics. You know what I mean? You gotta be, if you're doing math and physics, you gotta be worried about this alley dweller. Gonna beat you up. Anyway, We got over it. Okay. And so anyway, so it's 50% of whatever this vector is, or this length. This length was 1.2. What's 50% of 0.2? 0.6. 0.6 what? 0.6 meters. And did we get close enough? Because our actual distance we pulled this was 0.5. Well, so now we can just say, well, does that, so here's what you should always do in physics. Does this increase our angle? I think it does. I think if we actually reduce this to 0.5, our angle gets steeper. So now we'll do the cosine of 70 degrees. You know, I don't even know what that is. But anyway, and that's how you can do that. So that's sine and cosine. And I'll just do cosine right here. So if you have cosine of A, that's that hoodlum in the alley. So that's the x divided by the hypotenuse, which is L2. Okay, we're saying that this is L2 because it lengthened to a that's what it was anyway. All right, so and when this is 0, when the angle is when the angle is 90 over here, cosine of 90, well, this x is 0. So if we have cosine of 90, that's just going to be 0. So to get this to be 0, our x has to be 0 because that's 0 over L2. Cool. And then cosine of 0. So if we pull this out to infinity, our angle gets real small, almost approaches 0, and our cosine, our x, is real big. Our x is, yeah, our x is huge. But in that case, oh, so what I misrepresented here was the fact that I don't think I represented this right. Sure, if you pull this out to infinity, your angle is going to be almost 0, and your x and your length are about the same. So if my angle is 0, my x is equal to my L over 2, and because cosine is adjacent over hypotenuse, that's basically L over 2 over L over 2. And even though it's no longer 1.2 meters, but L over 2 over L over 2 is just 1. So when you pull this out, the ratio of this length to that length is 1. It's 100%. It's 100% of that length. And again, you should always go back to be like, hey, if I pull this wherever, my angle here is basically we're saying, let's say this is our new length, our L2 is over here. We're basically just saying, hey, this component, how much of this component is this length? And about 90%. So if I drew a line right to here, this distance right here would be about 90% of this line, maybe 95%. And perfect. So I think we did that. Okay. So moving on, but now we can get the right answer, and but we have to know something about tangent. Well, but I said tangent. See, this is where I was just like, well, hell yeah, tangent is just sine over cosine. So whether you need, let's say you just pick this angle again, it's sine over cosine, but we already know what those are. Well, we said the sine is just is this sunshine part, L, divided by L2. And we're going to take all that. And this is fun because this is where you get to use a little math kind of trick. So now I'm going to be up here, but and then divided by cosine, which is just that hoodlum divided by L2. Okay, and then so anytime where you have a fraction divided by another fraction, we're just going to say it's the first fraction, L divided by L2, multiplied by the, you just flip-flop this. So it's instead of x divided by L2, it's L2 divided by x. So that's all I did there. I just said, hey, I have a fraction divided by a fraction. I'm going to take that same fraction and multiply by the reciprocal of that. Cool. And once I have L over L2 times L2 over x, the L2's cancel. And, you know, this is what math and physics is all about. I mean, you really should spend 3 hours on one problem because you just reiterate the basics. And if you don't think you could just spit out these basics in your head, that means that you should use this hour to do that. You know, that's why physics problems truly should only be 3 problems a week, but you should be going back to all the basics on every single problem and getting up to this point where you don't know. You know, it's kind of the wax on, wax off. But anyway, we get L. Oh, damn it. Thought I messed that up. Anyway, the L's 2 cancel, and we get L divided by x. And that's literally tangent. So we got tangent of the angle is equal to L divided by x. Amazing. Amazing. All right. Hell yeah. So now what we would want to know is this is fascinating. I mean, we can find this angle. Oh shoot! Now I feel like I'm really messing up. But I kind of want to just use this Pythagorean theorem again. Because if we said the force was in this direction 6.6, this should say that 6.6 squared is equal to the component in this direction squared plus the component in that direction squared. But I guess we just don't know the ratio of the components. So I don't know why I'm having an issue with this, but the that's what tangent is. Tangent is basically saying the ratio of this divided by this. Now, all bets are off on this one. Tangent is not between 0 and 1. And 1. It's between 0 and infinity. Now, why is that? Because let's say L is never going to change. This x can be 0. Okay, so if x is 0, that's the infinity. This angle, this ratio between length and distance is infinity. If x goes to 0, your tangent goes to infinity, and I think that's just, and I think that's because your angle goes to 90, and if tangent of A is just equal to sine A divided by cosine A, and so that means tangent of 90 degrees is equal to sine of 90 degrees divided by cosine of 90. Well, we know that sine of 90 is 1, but cosine of 90 is 0. So you get 1 divided by 0 and you get infinity. Yep, I didn't spell that right, but I'm just going to end it there. So yeah, holy Toledo. And if you take this L, so I mean you take this X, you could pull it out to 1L or 2L or 10L, or you know, you could pull this particle out as far as you want, and you could pull this particle to infinity. And then the ratio between L and X would be 0, because L would be nominally small and X could go to infinity. You'd have a number divided by infinity is 0. So yeah, that's where this tangent's between 0 and 1. But as drawn right here, it looks like L over X, looks like L and X are the same. So this ratio is just 1. But like we said, this particle is going to be right at 0.5. So this ratio of L over X is basically 2. It's a 2 to 1. L is twice as much as X. And if we actually do it, that's going to be L is 1.2 divided by 0.5, and we get 2.4. So the tangent of this angle is just the ratio between L and X, and we get 2.4. That's the crazy thing about sines and cosines. Sine is just a component that's like the percentage of this length in this direction. It looks like right now that this is about 75%. You know what I mean? For a 45-degree angle is about 71%. You know what I mean? But tangent is always kind of an interesting one because you have to kind of choose an angle. You know what I mean? Because you could say that the angle is over here, and then you'd get the ratio of X over L. But what we're doing is get the ratio of L divided by X. All right, holy Toledo. Now, can we move on from here? Now how would we do the Pythagorean theorem? I mean, if we really wanted to do that. I'm going to try a tricky way to do this. But I'm going to say that 6.66 squared is equal to, and I'm going to call, let's see, if this vector is 2.4 times this vector, I'm just going to say that this is all equal to our force in the x direction squared plus our force in the, well, we're just going to say it's the same force in the x direction, but it's 2.4 times the force in the x direction squared. Whoops. See, this is interesting because like we like honestly, what you would just do is just do the inverse tangent because because you have the ratio between L and X. This is why tangent's neat, because if you know the ratio between L and X, you can find this angle. So let's just do that. But this probably would work, but I'm not gonna I'm not gonna attempt that. Anyway, I just got hung up, and this is my pace. So hopefully you're kind of faster than me at this. But what we're gonna do is arc tan is equal to arc inverse tan. I need to go to the internet. Atan, arctan. It's just atan. So we're going to do atan of this, of 2.4. Booyah. And this is in radians. So now we actually need to know what the hell a radian is. Well, a radian is I should say this. How many diameters are in a circle? How many diameters are in a circumference of circle? And you should be like, there's about 3. That's a good guess. About 3, and then exactly 3.14159. You know, blah 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 is pi. So that's how many diameter. What the hell does that even mean? If we had a circle and we just took the diameter out of a rope and then draped that diameter around the circle, we would have to have 3 of those diameters, 3 ropes draped around a circle to get 1 full circumference of a circle. So if we had a circle like this and we took the radius and made a rope out of the radius and had about 6 of them, it would take about 6 to go all the way around this circle. And the rope is literally 1 radius. I'm doing quotes right now. So the radius, and then this distance is 1 radian of an angle. So like it's about 60 degrees. Because if you take 360 divided by 6, you'll get 6 60-degree increments. But there isn't 6 radians in a circle. There's 6.28 radians, or 2 pi. 2 pi. So how the hell do you do you convert between radians? Well, even just right here, it says, hey, we got 1 radian. So what we just did was we said that there's 6 radians in a circle. This is really good to know. Like I'm gonna even make this red. 6 radians in a circle, and we said there's 1 radian. We had 1 radian, so it's about 60 degrees, because we know that 1 radian is about 60 degrees. So now we know our angle is about 60, but we actually want the exact angle. So how do we get the exact angle? Well, whatever radians we have, we're going to divide by 6, or 2 pi, and that's going to give us I don't know what the hell that's going to give us. Oh, that's going to give us the revolutions, because that's actually easier to do. Is like, hey, if I have 6.28 radians in one circle, that's 1 revolution of a circle, and I only have 1.16 radians. So the first thing I can do is just take this number, and it does it in 2 steps. Take this number divided by pi, which is that, and this is how much of a circle. We have 3/10 of a circle. I mean, we can visualize that. If this is 1 full circle, this is half. This is I feel like that's not right. But now I just have to multiply this by 360. So we're going to do this by 360. 130. Yeah, I made a mistake. So oh yes, I didn't divide by 2 pi. That's where the mistake was, because you got to divide it by 6. That's why even just pi is a stupid number. Because let's say I just took this divided by 6. You know what I mean? I could have got there a lot easier. So 2/10 of a circle. Here's 1 circle. Here's half. Here's a quarter. Here's so this is 0.25. So 0.2 is just right there. So it's about 60, 65, 70 degrees of a circle, and that's what we did. And is 67.3 degrees. All right, hell yeah. So now we know the degrees of this. Now this is real simple. You can do this like just in 2 seconds. But what we're doing is just kind of getting back to the basics of like why you would do that and how you do that, and learning about sines, cosines, and tangents. Okay, so now we can use our definitions for sines and cosines. Sine being this sunrise in part, and cosine being the hoodlum part, the adjacent part. And we want to know the force in the adjacent part. Cool. And we said if our particle's right here, the adjacent part's much smaller. It's less than a half. You know what I mean? Because we already did that estimate. So we're going to take the angle that we got. So we're going to take and let's say the cosine of that angle. What the hell does that even mean? So we got an angle of 67. So if you have an angle between 0 and 90, we already did that. But our angle is going to be 67. So cosine of this angle is going to be the percentage of this component in this direction. You know what I mean? So that was not easily said, but cosine is it's a percent of the whole. So that's why, you know what I mean? Yes, sine of 67 degrees is going to equal 0.4, or I don't even know, but it's going to be about 40%. 40% of this of this total vector. So, and we said the vector is 6.6 of what, newtons? Yeah, force, 6.6 newtons. So we're basically, so all that was just enough to be like, hey, divide this by 2 is about 3. So we're going to get about 3 newtons, you know what I mean? And now let's finally friggin' do it. So we're going to take the sine. Now you gotta get this back to radians. That's the crazy thing. Well, it already was in radians. So yeah, in Excel everything's got to be in radians. So there's our angle. We're gonna go equals sine of this radians. Okay, yeah, it's about 1 radian. Because 1 radian's about what, 70 degrees? I don't even know. We can find that out. So so if we have equals 1 radian divided by 2 pi divided by 6, basically, 2 times pi. So that's the revolutions of a circle. And then this times 360. So it's 57. Yeah. So it's, how do we have less? How do we have less? Oh, no. Our radians is, excuse me. Our radians is 1.17. Yeah. So our angle is 67 degrees. And what the hell do we even just put right here? We said the sine. Oh, we don't want the sine. We want the cosine. I apologize. Yeah, we want the cosine part. It's 0.38. Yeah. So it's 38%. So we're just going to do this number times 100. And then get it to where it's just a percent. Oh, shoot. Okay. We're just going to do this. Yeah, they even have this on that 38%. So 38% of what? And then we have our 6.6, this. So we're going to do this times 38%. Booyah. So it's 2.54 newtons. Okay. And this is doubled up. This is both springs. So just to let you know. Both springs. Hell yeah. All right, so 2.4. So now we can do that initial guess. Let's say there's a force of 2.56 newtons on this Nalgene, and it's just constant. You know what I mean? It's a constant 2.56 Newton force until it crosses this finish line. Cool. How fast is it going to go? Well, you do that same thing right here, 2.56. And you throw this in. So let's do it. It's 2.56. 2.56. And what you would get is the velocity equation would be 2.56t. And the acceleration equation would be 1/2 of 2.56, which is equal to 2.56 divided by 2. Is 1.28. So you'd get a position equation, 1.28 t squared. Oh, I don't even know why I had that point. Oh, anyway, there you go. So there you go. So now what can we do? Well, you can. We want to know the velocity. So we have a velocity equation in respect to time, but because we integrated again, we got a position equation. So you should, anytime you get an acceleration, you get the acceleration because you got the force. And if you get the acceleration, you can just integrate acceleration as a function of time and get the velocity, and integrate velocity as a function of time and get position. And the cool thing about position, we said we pulled this back 0.5 meters. So in that's where the 0.5 was. But anyway, so that's why even these constants integration for this right here, we got rid of the plus 0.5 because we're just going to say this is our new 0. Our 0 is right here, and we're going to even say this is the positive direction anyway. So we're just going to say when x when x is 0.5, solve for t. So what was t? Well, you would do x. You would do 0.5 meters divided divided by 1.28, and then you take the square root of all that. Oh my god. Cool. And I got to get rid of this because we're just going to do that right now. So we're going to go equals square root of 0.5 divided by, and we got to get very specific. So we're going to take this Newton, but we got to divide that by 2. If we divide this by 2, yeah, well, I don't want to get mixed up. But yeah, so we got that divided by 2. And what else? I think that's it. And we took the square root of it. Perfect. So now this is our time. This is the seconds. It would take, with that constant force, it would take 0.6 seconds to get here. And now we can find our velocity at this point because our velocity at that point is just 2.56 times t. So we're going to go, and 2.56 is just this number times our time component. Booyah. So our velocity is 1.6 meters per second. So that took about an hour and a half. I don't even know how long we're going. But this was the first guess. I mean, this you could just crush out in about, 5 minutes, 2 minutes. You should be able to get this guess. Because all we did was found a force. We found the initial force. We said, hey, guess what? Initially, there's going to be a force on this ball of 2.56 newtons, and it's going to be in this direction. So we're just going to say, hell, that's going to be constant, 2.56. And we're just going to use our equations of what we know, our integrations of velocity, integrations of position, and we're just going to get an initial guess. But what we know about these springs is the second it gets to about halfway, the force on this spring is going to be less. And actually, when this particle gets to here, the force in this direction is 0. It's in equilibrium. Even though it's got velocity, there's still no force on this particle. And Newton's law said even though you have a particle in motion, if there's no force on it, all that means is the particle is just going to keep going in motion. A particle with velocity is going to keep going with its velocity. Okay, so here's the second guess that you can usually do with all problems. We said at the beginning of this thing, there's going to be the max force, which is 2.6 newtons. But we said at where we want to take our measurement for velocity, our force is 0. So why don't we just take the average force? Let's just say instead of 2.56, there's just an average force of 1.25. You know what I mean? So we're going to get the average. We're going to go this number. Where is it? This number divided by 2. Yep, so there you go. Meters per second. So now we got 1.28. And now we're going to do that same thing. So we're going to take our seconds is going to be the square root of, so this value goes to 1.28. Our seconds is going to be, I feel like we messed that up. If this is our acceleration, half of it is going to be this divided by 2. Because that's going to be our position equation is now going to be, our new position equation is 0.641. Okay. And you're going to take the square root of 0.641. Yep. Yeah, to get the time value, you're going to take you're going to take 0.5 divided by, yeah, we did it. I don't know why it's going to take, oh, it takes more time. I'm sorry. I got confused there. It takes more time. And then if it takes more time, now we're going to throw our, so we got to take our velocity equation is this acceleration times time. So booyah. And now we get 1.13. So it's better, but we do know from the back of the book our answer is 0.834. And you might be like, why the hell have I watched this video up for like 2 hours and to get like a dumb answer? Like an answer that's not even going to give me any credit. But it at least, in physics with guessing, it's like, hey, can you get like an accurate guess? Like this guess does tell us something because we know the halfway point. Just by geometry, the force is going to be high here, but then almost virtually zero. Because let's say it's because like this swings out in like a circular motion. You know what I mean? If this spring did not lengthen at all, it would follow a circle just like this. And see how this circle like basically hits the horizon and stays here because it basically makes a tangent with this horizon. So it's literally, there is zero force on this. So we said at the halfway point, our force would be half, but that's so not true. Basically, our force at the halfway point is zero. So now we can actually use that knowledge, so we can actually maybe come up with a way to underestimate, because we're still overestimating our velocity. So let's say our force at the halfway point is zero, because this is cool. Because now because if our force at the halfway point is zero, there's no more force. And if there's no more force, there's no more change in velocity. That gets back to F equals ma. If we lose our force at the halfway point, we lose a change in velocity. So F equals mass times dv dt. And that's why dv dt just looks like you're doing calculus and your mind explodes. But anytime you see this acceleration, you should, in your mind, be like, hey, acceleration is just change in velocity. So if our force goes to zero, our acceleration goes to zero, and there's no more change in velocity. So we're going to get our max velocity at halfway. So we're going to use the same equation and say that our force is our force is still yeah, our force still goes from 2.56 to 0, and we're going to say that our force average is still this, so this is still going to be our force average, but our distance is only going to be 0.25, because at 0.25, so we're going to go right here, 0.25, and that's all that did. So now our time is real slow to get there. But our next equation that says what does this say? Yeah, that was weird how this worked, but no, our time is way less. Our time is much less because our it's, I don't know if it's half as less. It's only the square root, so it's not half as less, but our velocity sure reduced, and now we get 0.8 meters per second, and that is more. So this probably is the golden moment of this math video, because you're just like, oh, you're guesstimating, and you're actually seeing that if this spring did not change length, it would follow a circle. And what we know about circles is basically there's zero change in length through here. And then once it starts to curve up, then we get all of our change in length just almost like right in here. So that's where we're going to get force. So this particle is going to have force on it this direction, but once it gets to here, there's going to be no force on it. And sure, there's a tiny, tiny bit of force, but this gets us a more accurate guess. And I'm going to this is just 0.8. This is just 0.8. So I'm going to go now. I'm going to try to get the average between 1.13. And how do we do averages again? You take this 1.13. Add it to our other number, which is 0.8. And then divide by 2. So this is the other physics equation that you should get used to. And see, that's still way high. That's crazy. So the 0.8 equation, let's just go back. Whoa, we got to go the other direction. Nope, we can't do it. So we got to go here, 0.25. I definitely want that to stick. So 0.8. And our actual answer is 0.834 or something like that. Okay, so now we're ready to actually do kind of what I came to do, which is we identified the force. Why we use an Excel? Because we can identify the force at this point and then basically kind of use this, figure out our force, figure out our acceleration, and if we can find our acceleration, we know that's just change in velocity over a very small amount of time. And then if we know our change in velocity, we can figure out our change in position. And then upon our new change in position, then we can find our new acceleration. So holy Toledo. And I think I'm just going to go right here to do this. So we're going to do time, and we're going to go 0 because it only takes 1/8 of a second. We're going to go time is 0. We'll just do 0.1, 0.2, just to make it super simple. And then perfect. So that's our time. Now we want to know, and then maybe we'll just throw mass. Mass again is 1.2. No, it's 1.18. 1.18 kilograms. Is that right? Length is 1.2. And then see now you can look at this equation and see where and this is using the potential energy, which is the force times this distance, and we're not even going to use that. That's for another. All we want to know is like, hey, they want to know what the velocity is. So cool. We're going to find the velocity. All right. So now you're going to have x, and that's going to be I think we're just going to go 0 on the x, just in meters. We're going to say that this is 0. Okay, and now we need to know the length of this this spring, which is so L2. And what the hell do we say that was? The Pythagorean theorem. It's this. So x has to be 0.5. Sorry about that. Perfect. So Pythagorean theorem says square root of this x squared plus this L squared. And L squared doesn't change, so you got to do F4. F4, and that changes it into dollar signs. Booyah! So now we have that. Now you can find dl, which is the delta L, which is equal to the absolute value of this minus this. Oh, I feel like we did something wrong. What the hell did we do wrong? Yeah, why was this 0.3? Oh, we didn't square it. Cool. Beauty. All right, so now we got that. And we will have to kind of just trickle over here. So now, because we have the change in length, now we can find the force on the spring. And I'm just going to do this. It's KD, KX, KL2, KDL. Yeah, because it's the spring constant. So now we need to know the spring constant. And we already did that. It's 40 newtons. And now we know what the hell it means. So that's cool too. All right, so we got K times, whoa. And our K, I don't know why, oh yeah, we got to do dollar signs because that doesn't change, times our DL. Cool, enter. Yeah, we got 4 newtons. And we're just going to double it up right here. We don't want to do, it's always going to be 2 because there's 2 springs. So 8 newtons. All right, that's in newtons. This is in meters. Meters, seconds. Cool. All right, now we know the force. So we use F equals ma to find A. So we say A is equal to F divided by m. Perfect. So that's going to be this force divided by our mass. And our mass doesn't change, F4. Beauty. Okay, so we got that. 6.79. I feel like we did something wrong. 1.18. How did we get 6.6? So we can check our errors doing this twice. What the hell? 1.2. We said it was 1. Yeah, we were off. Yeah, we were off too. So let's change this to 1.18. And that will change some of our values. 1 point. Yeah, it changed it a little bit. Cool. And it made this a little bit faster. So yeah, that is more representative. Cool. And it's just interesting. And you could figure out that an average force, like the force isn't going to go to 0 at the halfway point. It's going to go to 0 at the 0.45. You know what I mean? The 55% of getting there. You know what I mean? So at some point, you can say, hey, that's going to be the point where averagely it's going to be, you know, if you did a linear, if you said the force was max to 0, it would be a linear from here to there. So yeah, you're just taking, you know, something that's curved and trying to box it in and make it a linear relationship. Okay, all right, moving on. So now we found the acceleration. Cool. What the hell is the acceleration? That's dv. That's change. That's change in velocity. Okay. Damn it. All right, dv. Perfect. Okay. So now, how much does the velocity change actually? So no, acceleration is dv divided by dt. So all we want to know is change in velocity, but we're only going to go a 1/10 of a second increment. So dv, and this might suck. This might suck. This might be where you get hung up because acceleration is change in velocity, dv divided by change in time. That's literally what it is. So this is an equation. So now we just say, hey, I want to know what my change in velocity is. Well, that's just equal to your acceleration times dt. Didn't want to write an 8 there. Apologize. Okay, hell yeah. So literally, dv is just our acceleration, which is this number, times our dt, which is just 0.1. So, and I'll just do this. It's just this minus this, and then we'll just put it on blast. Okay, so this is our change in velocity in meters per second. So in our first 1/10 of a second, our change in velocity increases by 0.67 meters per second, which is significant. I feel like I did something wrong, actually. Oh, yes, I did. I definitely did something wrong because we said the force is 8 newtons, but the component of the force, that's where I get confused on this all the time. I'm saying the force in this spring is 8 newtons, but the component of it is only we just need to know the cosine. So we need to take this 6.7 times the cosine of whatever angle that we have, and the angle is actually a tangent, is the tangent to the -1, or the atan. I'll just write it because that's how they do it in Excel, is atan of x over L, or no, L over x, opposite over adjacent, L over x. So that literally is the one-shot pony for this. And since we already went through it, let's see if we can just do that. So now we want to know F in the spring direction. We're going to call it F of S. No. We want to know the F of X. We want to know the force in the X direction. Yeah, for the love of God. Okay, and that's going to be equal to this total force, 8 times cosine. Of A tan of L, that doesn't change, so you got to do the dollar signs, divided by X. And I might have this wrong, you know what I mean? Hopefully I got it right, though. And then we get 3.07. Is that kind of what we got? I don't think so. Yeah, we got this. So how did we do the tangent? L over X is 2.4. So H tan is the radians. Should have worked, though. Oh, I don't know why I can't click anywhere. Uh-oh. I think I might have to... Oh, there we go. Okay. Huh. So we have the force. Yeah, let's just do A tan of L over X. Yeah, 1.16. And then cosine. Oh. Cosine of that angle. 38%. And 0.38 times 8 is 3.04. Yeah, so we're totally right, and I don't know where we kind of made a mistake and only got 2.6. I think it's here. Let's find out. Oh, because that was wrong. 1.18. Oh, yeah, because our acceleration. Oh, our force. Oh no, this is interesting because we found our acceleration. Also, that's the thing. It is we just did it in reverse order. So now we said the acceleration. We said the force is only 3 newtons in this direction. So maybe it's just a different way. Because force is a vector, also acceleration is a vector, velocity is a vector, distance is a vector. You know what I mean? So you can whittle it down to whatever component, and as long as we're working in the component in the x direction, so we have 3 newtons in the x direction, and then that means the acceleration in the x, and so we're just going to put a of x right here, capital A of x, just to make sure that x doesn't look funny. And now this is going to be this force. Whoa. So we got to change this to Z3 to AA3 right there. Booyah. So now, perfect. So now our acceleration is 2.6. Now that is still different than what we got. But no, it's 2.6. So yeah, now we're cooking with butter. And we're doing this problem twice and finding little errors. So that's good. So now our change in velocity is only 2.6. Perfect. But now our spring moved. Oh yeah, so if that's our velocity, so we went from, so now you got to go. We went from 0 to 0.26. So now we definitely need to get our velocity average. Our velocity average is going to be our initial velocity, and damn it, I almost need to put like another line in here. But we'll do it the next step. So basically, it's just this divided by 2. I apologize for doing that, but now we can find our x, our new position. Oh, because I don't have a 0 here. Yeah, that's crazy. I need a basically almost a 0 here. So we need, I don't know if this will mess us up. 0 and then 0.1. That shouldn't, because now we'll just insert this. So we're actually gonna, what is our velocity at this point is 0, and then our change in velocity is 0.2. So now we're good to go. So now we can go, our v average is, so this makes more sense. It's our velocity at this, sorry, it's our velocity here, plus our plus our increase, and then divided by 2. So our that's interesting. This does do 2 equations. So velocity average. So the equation that we're using here is our velocity plus our change in velocity divided by 2, like all divided by 2. I'm not going to put the parentheses, but damn it, put the parentheses. So this is our, no, that's not right. That only works if this is this. That's absolutely not right. It only works if your velocity is 0 at the beginning. So the velocity at this point is equal to, so now we know our change. So our next velocity at this time is going to be our initial plus our change in velocity. Okay, so now our velocity average is going to be this 0 plus this new velocity divided by 2. Okay, so now that's 100% makes sense. Because this is our average velocity over this 1/10 of a second, we can find our distance, because our distance is equal to 0.5, but now you just have to know it's minus because our velocity is in the opposite direction. So we're subtracting our velocity average times our dt. And does that make sense? Our position, our dx, and I should just do a dx. Our dx, our change in position is or how about our velocity average is just the equation for velocity, which is d is like a change in position, change in time. And see, this is where these are infinitesimally small, but it's just also delta x divided by delta t. Because it's our change in position divided by change in time. So it's like if I say I went from here to the next town 60 miles away and it took 1 hour, my velocity is 60 miles per hour. So 60 miles divided by 1 hour, 60 miles an hour. That's my average velocity, because I could have gone faster to pass cars and slower, and I had to stop at some stop signs. And so, but that's where I love this average velocity, and you use it a lot, especially if there's a linear relationship. Anyway, so that's how you get this change in position. Oh, whoa. So maybe I just do need to do dx. Our change in... Oh, so this says our dx. So if this is an equation, our dx is just velocity average times dt. Perfect. So yeah, so we're going to go is our velocity average times dt, which is this minus this. Booyah. So this is our change in position. And so our new x, right here is our initial plus, or no, minus our change in x. All right, perfect. So we hardly moved at all. And then our L2, see, this equation was with our x, and these dollar signs say that don't change, so we're just going to pull this. So our new L2 is a little bit shorter. So now we're here, and it's a little bit shorter on there. So our change in L is a little bit, that did not work. Okay, see, I didn't need dollar signs in this one. So you go up here in F4. Whoa, 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 whoa. Booyah. So it's just a little less than a tenth. And then our force is going to be just a little bit less. Our force in the x direction, just a little bit less. Our acceleration in the direction, our change in velocity is going to be a little bit less. And so our dv, our change in velocity, is going to be a little bit less. So then our average velocity, so let's see what this average velocity was. It was our, so if this is our change in velocity, then our new velocity is this plus that. Oh shoot, I feel like I ran into a brick wall here. Let's just pull it down and see. Yeah, I mean, yeah, our change in velocity is 0.24. You know what I mean? So in a tenth of a second, we're getting, now we're almost halfway there. Okay, so yeah, I was just shocked by our velocities almost approaching our final 0.8. But anyway, so this is our change in velocity. So at 0.2 seconds, you're going to get this. But now we need to figure out how much distance we traveled, and so our velocity was 0.26. It went to 5. We need to find the velocity average, which is this plus this divided by 2, and see how 0.38 is kind of right in between these. That's going to be our average velocity, and again, our velocity average is equal to dx dt. So I should write, dx right here. Here's the equation. Let's highlight that one, because dx is velocity average times dt. So we're going to pull this down, and so this is how much we travel again. It's we travel. We have this velocity, 0.38, but we're only traveling for a tenth of a second. If we traveled for a whole second, we'd go 0.38 meters, but we're only traveling for a tenth of a second. Okay, so we're only traveling to here, and that's going to be our new x position, which is this minus this. Okay, hell yeah. And now we can just pull these down. So this is going to be a little bit less. And you don't have to pull these down one at a time. I mean, you can just pull a whole system of them down. But this is kind of the order that you would pull them down in. And so now what happened? Our velocity increased to 0.69 because our acceleration definitely dropped. It went from 2.6 to 2.4 to 1.9. You know what I mean? So now let's pull them down again. And there you go, 0.8, 0.824. So and it only took 0.4 seconds. Now this is super rough and average, but so even at 0.3 seconds, our acceleration is down to 1.8. So we're still accelerating, and our distance is only 0.3. So we haven't crossed that goalpost. And so let's just pull all these down, because now when our position crosses the goalpost right here, this is past the equilibrium. It gives us our information. It says it takes 0.7 seconds to do that. And how long did we say it was going to take? Because we got a pretty accurate guess, 0.619. Okay, so keep that in mind. And so yeah, 0.7 seconds. We crossed equilibrium. Our velocity is 0.925, so that's high. But I mean, in the grand scheme of things, I mean, that's close enough. I mean, the answer in the back of the book is 0.8, and we got 0.9. You know what I mean? Who cares? And we only did like 10 iterations. So now what we're going to do is we're going to go 0.01, and we're going to shake and bake this down. But the other thing is that anything that was related to, okay, and so, oh, no. So I think we're basically just good to go. We just need to pull this down hella. So we're going to take this. I mean, you need to pull it down about 10 times the distance. We're going to pull it down to there. I mean, because you need to pull it down to 0.7 seconds. And now you're going to pull all these down. All right, that should be plenty, because our equilibriums are right at that 0.7. So right here it says 0.79. That's our new equilibrium. And let's see what do we want to know? We want to know the velocity, AC. 0.8329. 0.8329. And if you bear with me, I'm going to go to the back of the book just to look at the answer, just because we're going to do maybe one more iteration so you can get the exact answer. So this is problem 47. I'm almost there. 0.823 is the meters per second. 0.8. Oh wait, look. I don't even know what I just said, because I think I'm just basically reciprocating those last two numbers. I mean, we're super close, but 0.823. So 0.823 is the actual, and we got 0.832. So we'll just do the same thing. Now we're going to go 0.001, and now we're got to crank this down to 0.7. So it's all the way to. I mean, you don't have to go too far. I mean, it's about 1,000 of these things. But it's not that big of a deal. And now just pull all your numbers down again. And the cool thing about doing this is once you got it set up and it's working properly, I mean, you get real crisp numbers, and you can the only thing that this isn't telling you is this isn't set up. I mean, we can only cross the finish line. I mean, it's not gonna. I don't think it's gonna bring the object back. That's the only issue with this way of doing it. Hopefully that didn't mess it up. I don't think so. I don't know why I feel like that messed it up. Okay, so find our equilibrium where x is crossed to 0.8 seconds, and AC, and now it's 0.824. So there you go. So highlight that velocity, 0.824, and our actual answer is 0.823. So doing it this way, it's still not exact, but we're approaching the exact number. And, you know, we're hella close enough. And the cool thing about setting this up in Excel, I mean, it's just the same as an equation. Like we know the velocity at every point. It's actually a series of equations. So here's your velocity equation, and here's your position equation. And yep, so there you go. You can fill those. Oh, I don't know what I'm trying to do. But anyway, I'm basically done. And and if we go back to actual, their equation has an x, you do have x squareds in here, so it is going to take into consideration passing the equilibrium, and the force should return the other direction. I think, you know what I mean. That's what you would want. I just set one up to go from here to cross the finish line. But I don't know if I would have to run another, iteration from, have my initial velocity once it crosses the center line, and then have the forces do the same thing, but in the other. I don't know if I could actually model a cyclical thing, going back and forth, back and forth. I guess I could. I could try. We're going to give it one go. So I'm going to go 0.01. We're going to go a hella lot of numbers. So we're going to go about 12 seconds. No, it just goes. It gets to a. No, it just blows up. Yeah, so this doesn't work at all. That from that perspective. All right, but hell yeah. But I really like doing this with any problems. It goes back to the basics. F equals ma, and this isn't energy. This isn't even an F equals ma problem. It kind of is. You do have to identify the force, but then you identify the distance. And so what this says is could I even visualize that? There's a force on this ball. Yeah, that's kind of an interesting thing. It's kind of what we did when we tried to figure out the average force, because we basically said that hey, there's going to be an average force on this Nalgene, and so if we can find this, and I'm doing quotes right here, quote unquote average force, we know the distance that we pulled it right here. So cool. And the distance we pulled it is a fraction. So that's where this is. This is your L change in L. So what the hell is this? X squared plus L squared, the square root. That is this distance. So right there they have L minus this. You get a negative. You actually get a negative here because this is going to be a larger number. And so here is your delta L. And what we said was our change in distance times our spring constant times 2. That's going to be the force. But then they're also saying that it's another factor of L right here. So basically, working this equation out, work is force times distance. And let's do capital L. And our spring constant says our force is equal to a spring constant times d. So and let's say this is work. So that means that work is equal to K times D times D. So work is equal to K spring constant times D squared. You know what I mean? So essentially that's where, and D is just X. So spring constant, so it's KX squared. That's kind of what you're getting. That's going to be the work involved. And again, I want to solve this from a calculus perspective, but hell no. I'm just going to say that's going to fry my brain, and I'm just going to spend way too much time not learning about anything by just trying to do the magic trick of getting an integral like this. Because I think you do need to integrate. Maybe you don't, but I think you do. But maybe you don't. I don't know. That's for another video. But any of these physics problems, if you just know the basics, F equals ma, a just means change in velocity. Hell yeah, you can set up a change in velocity chart, and then just pick some sort of incremental change in time, because anytime you have a force, it's only for that little moment in time. And so what we did was we found a force for this moment in time, and it was operating on some sort of mass. So that means that this mass changed velocity for that short period of time. We can find its new velocity. From that change in velocity, we can find the velocity average, multiplied by this, again, short little period of time. We can find its change in position. From that new position, we can do the same steps over and over again, and we can figure out how far this thing's progressing, how far the velocity is increasing, and why is the velocity increasing or decreasing? Because that means that it's accelerating. If the velocity is doing something different than just staying constant, it's changing its velocity. That's the literal definition of acceleration. Acceleration is some sort of change in velocity divided by some sort of change in time. And typically, it's whatever the velocity is changing divided by 1 second, because it's always in meters per second per second. Acceleration is not always in meters per second per tenth of a second, or meters per second per hundredth of a second. But you could say, you could just do that, like Dominic Toretto. If he's going 0 to 60 miles per hour in 1 second, sure, his acceleration is 60 miles per hour per second. His acceleration is a change in speed of 60 miles per hour in 1 second. So let's say his acceleration is the same, and you want to know how fast he's going in a tenth of a second. Well, in a tenth of a second, he's already going 6 miles per hour. So you could just walk right next to them for about a tenth of a second, and then he's on his way making 12 movies a year. All right, so anyway, we're going to wrap it up there, and it gives you the full, hopefully this recorded. And are we still recording? Because I got to say my goodbyes. Thanks for joining me. This was sweet. 2 hours, 22 minutes. It was such a worthwhile video. All right, that does it for me. Thanks for joining me.